question to address with this molecule is, does it have pseudo-asymmetric centers? And if so, what are they? So a pseudo-asymmetric center must have a plane that bisects a stereogenic center through two substituents and their bonds to the center. Well, as you can see, we have that with this molecule. Then, are two of the substituents attached to the center constitutionally the same, but configurationally different? Well, clearly they are constitutionally the same, but the ring leads to the same thing from either direction. So, isn't that configurationally the same? Let's look at this more closely. Let's examine this carbon. We will lay the molecule out starting with this carbon and first look anticlockwise along the ring. From the digraph location, we will call this the right group. Next, the aiming group coming out of the screen will be described from the digraph as top. Then, clockwise along the ring will be placed on the digraph to the left. And finally, the hydrogen going back into the screen will be positioned at the bottom of the digraph. If we consider the atoms one bond from the red carbon of study, we find one nitrogen, two carbons, and one hydrogen. The top group nitrogen is the highest priority overall, so first highest group. The bottom group's hydrogen is the lowest priority overall, so fourth highest priority. But the left and right groups cannot be distinguished between each other on priority. As we look at atoms progressively more bonds from the carbon of study, we find that the left and right groups have all the atoms with the same atomic number, same atomic mass, no geometric isomers, neither group has diastereomers, no mixtures of pseudo-asymmetric and non-pseudo-asymmetric stereogenic centers. Thus, we arrive at the final priority rule to consider before concluding the groups are the same. So, is there a difference in stereogenic centers? First, we will inspect the orange carbon on the left as the digraph is laid out. Considering atoms one bond from the orange carbon, the amine coming out of the screen is the first priority, and the hydrogen going back is the fourth priority. The left and right attachments can only be distinguished between each other with atoms three bonds from the orange carbon. The left attachment has no atoms, whilst the right attachment has a nitrogen, carbon, and hydrogen. So, the left attachment is the third priority, and the right attachment is the second priority. The lowest priority is facing back, so it just remains to go from the highest to second, then third highest priority. It provides us with a clockwise direction, which would ordinarily be denoted as a capital R. These assignments of stereochemistry are themselves on a ring that's been theoretically opened up. When the ring opens, it can change everything. So, they do not necessarily reflect stereochemistry in the real molecule. Thus, they are given the descriptor AUX for auxiliary stereodescriptor. So here it is, capital R AUX. Now, what about the right group on the digraph? Again, considering the orange carbon there. The forward amine is the highest first priority, and the lowest fourth priority is the backwards hydrogen. Again, the left and right groups relative to the orange carbon can be separated in priority at atoms 3 bonds from the orange carbon. The right attachment has no atoms, whilst the left attachment has a nitrogen, carbon, and hydrogen. So the right attachment is third priority, and the left attachment is second priority. The lowest priority is facing back, so it just remains to go from the highest to the second, then the third highest priority. This provides us with an anti-clockwise direction, which would ordinarily be denoted as capital S. But under these circumstances, as we just discussed, it will be capital S Aux. Returning to the digraph centered on the red carbon. Now we know that the left group is capital R Aux and the right group is capital S Aux. Priority rule 5, as we've ultimately got there, tells us that R is a higher priority than S. So the left group is a higher priority, second overall, than the right priority, third overall. Now, this is where we need to be clear. The orange carbons on the digraph are the same single carbon on the real molecule, but approached from clockwise and anti-clockwise directions from the red carbon. The hydrogen and amine spatial locations are the same in left and right digraph groups. But at the left digraph orange carbon, left attachment is a shorter carbon chain, and the right is the longer carbon chain. The right digraph group has the shorter chain attachment on the right and the longer chain on the left. The left and right attachments are switched. To relocate two attachments and get opposite stereochemistry. So the same orange carbon on the real molecule is S and R, depending upon whether it's being arrived at clockwise or anti-clockwise, respectively, from the red carbon. Back to the original question. Are two groups attached to the red carbon configurationally different? Two of them are constitutionally the same, but going clockwise is S Aux and going anti-clockwise is R Aux. So they are not configurationally the same. So the red carbon is a pseudo-asymmetric center. But is it small r or small s? The highest first priority is the amine coming out of the screen. Then the second priority is the lower ring purple carbon, due to from there the configuration of the orange carbon. Next is the third priority, that's the upper ring green carbon, again due to from there the configuration of the orange carbon. Lastly, the hydrogen going back into the screen is the lowest fourth priority. The lowest priority is going back, so to consider the direction moving from highest to second to third priority, here that is anti-clockwise, which equates to S. but here that is small s, as it is a pseudo-asymmetric center. In the real molecule, if you do the full calculation, the orange carbon is also small s.